So for the rest of today, I'm going to talk about, since you guys have no problems, I'm going to talk about chapter 9, okay? And this is not going to be on this test, but it might be useful for some of you to take MCAT because it's like one part of the MCAT, okay? So if you look at the book, wait, sorry. So chapter 9, the title is fluid and solids, okay? So roughly speaking, the first section talks about, the roughly states of matter, and then talk about the two quantity called density and pressure, and then pressure difference and buoyant force, fluid motion, other applications. The first, this up to here is all about fluid. And then the last 3 sections, it talks about solid, okay? So in this class, I'm gonna talk a little bit about the fluid, okay? So that, basically give you guys like an outline about what the fluid is about. So I'm gonna try to use the rest of today to do that, okay? And then on Wednesday, I don't plan to do anything. I'm going to talk about the test 3 on Wednesday and also address questions from you guys, okay? So, another thing is if you haven't done it, please do the course evaluation for this course in the summer, both for the lab and the lecture, so that I can get some feedback from you guys and use that to improve my teaching in the future, okay? So let me talk about fluid, okay? So first thing, we need to talk about a little bit the states of matter, okay? So it turns out that for the same kind of material, it can stay in different states, okay? A very good example is a very common material we have every day, which is water, okay? As we know, if you put water in freezer, it becomes ice. And if you put water on top of a stove and heat it up, it becomes a steam, okay? So these are the same object, same material, but it has different states. So this is called solid, and then this is called liquid, and this is called gas, okay? So these are the 3 common states of the matter. Sometimes they're called phases, so phases, okay? So you could say every material has at least 3 different phases: solid phase, liquid phase, and gas phase, okay? And these 2 together are called sometimes fluid, okay? So when they talk about fluid, and they mean liquid and gas. And then we have also solid here, okay? Now what induced this change of the states is the temperature, okay? As you increase the temperature, material will go from the solid phase to liquid phase and to the gas phase. And actually this is true not only for water, but for everything else as well. Like the metals you use, they are solid at room temperature, but if you increase the temperature a lot, like to a couple thousand degrees, it's gonna melt to liquid, and then if you increase even higher, it's gonna become gas. So all materials are like that. It's just like the different temperatures you have here to have this phase transition are different, okay? So they are basically separate as all different. So for water specifically, this happens at 0 degrees in Celsius, and then this happens at 100 degrees in Celsius, okay? Well, in terms of Fahrenheit, this is 32 degree in Fahrenheit. Well, this 100 here, I don't even know what it is. 32, okay. Like you add 18 to it every time. So 400 is like 180. So it's gonna be like 500. I think it's 500. Yes. I think it's 500 degrees in Fahrenheit. Okay, you have this boiling water. Okay, so 180. Yeah, I think so. So anyway, we don't need to know a whole lot about this. There's definitely physics you can talk about. This is related actually to chapter 10, chapter 11, chapter 12. When we talk about thermodynamics, thermophysics, they're related to temperature, okay? And actually what determines these phases essentially is the microscopic interactions between the atoms or molecules in the material. And then as temperature goes up, those molecules moves faster and faster. So it kind of break those solids into liquid and then into gas. Anyway, so let's talk about a little bit about the fluid, okay? So you want to study fluid, basically it's liquid and gas. There are two fundamental quantities we need to introduce. They're called density and pressure. So the definition of them pretty simple. Density, normally people use rho. It's not P, it's a Greek letter, rho, okay? Defined as rho equal to m over v. So mass divided by volume, okay? So density basically is it's basically like a mass per unit volume thing. And as the definition suggests, right, basically it tells you how dense the material is. So if you have the same volume, the bigger mass you have, the denser the object is. And so this is in kilogram and this is in meter cube. So the unit for density is kilogram per meter cube, okay? It is a scalar because there's no direction associated with it, okay? Now, the book has a list of typical materials, density of typical materials. They're listed here. The easy one to remember is water. So the density of water is 1 times 10 to the third kilogram per meter cube. So it's like 1,000 kilogram per meter cube, okay? Now, as you can tell, see, this is 1 times 10 to the third, right? See, for those metals, they're normally heavier, denser than water, okay? So see, they go like 2.7 all the way to 19.3, or platinum is like a 21.4. They are more denser than water, okay? Those metals, remember, they're normally solid, so that's why they're denser. And well, the liquid here, normally there's a couple of liquid, they're comparable to the density of water. They're all kind of small, the density. Well, the gas phase is even smaller. See, air has a 1.29. It's like 1,000 times smaller in terms of density. Oxygen 1.43, et cetera, et cetera. These are all really small, okay? And this is very typical. Normally, the density of liquid is larger than density of gas and smaller than density of solid. Well, there's one exception. Ice has a little bit smaller density than water. So when water freezes up, the density actually getting smaller a little bit, okay? And that's why the volume gets larger because mass is conserved. So if you put a cup of water and put it in the freezer, if the cup is like a full, then when it becomes ice, you observe that the kind of goes out of the cup a little bit because the volume increased. And that has a very interesting phenomenon later on we will talk about, okay? So, and also one thing you know is like the denser the material, normally it's more expensive, like gold, right? Gold is very, very expensive because it's a basically rare metal, has a really large density here. It's not very normal to have this density. Well, platinum, as some of you know, is even more expensive than gold. This uranium here is not typical. We don't normally have it because it's actually radioactive. It means it's kind of cause. It's gonna. It's not good for our health. Okay, but if you want to do like atomic bombs, okay, you need uranium. So uranium actually is pretty expensive as well. Okay, so okay, let's go back to this. Okay, so this is the first quantity, is density. Okay, this is a very useful quantity to describe the property of fluid. Okay, and the second quantity we need is called pressure. Okay, well this one is in P, is P. Okay, this is actually P, letter P. Okay, so it's defined as force per unit area. Okay, so we have force divided by area here. Okay. So when we talk about pressure, it's kind of like force, but it's not the force, but because the force per unit area. So it's like how much force you apply to a unit specific like areas. So this is actually also very good quantity to have because kind of tell you the property of this material, like how sustainable it is to pressure, to the force. Okay, so the unit for force is Newton, unit for area is meter square. So it's Newton per meter square for the unit. Okay, and there's a special name for that. It's called Pascal. And this name actually again come from a physicist that studied a lot of pressures. So that's the name of that. Okay. So what is how do we kind of understand why pressure is very important for us? Okay. For example, if you think about this example, right? Like you walk on there's snow here, right? On the ground, snow. Right. Now you try to walk on the snow, right? Now, if you just walk by your barefoot, I mean, or like normal shoes, right? You see that your feet goes into the snow, so it's gonna go in there, okay? Because, well, if you actually wear like a ski board or something, you're gonna stay on top of the snow. Now, what's the difference? In both cases, the force on the snow are the same, but basically equal to the weight of you. Okay. Now, actually, in this second case, you have even little larger weight of force because there's a weight of ski as well. But why you actually go into the snow in this case, while you don't in the second case, it is exactly because of pressure. Say same force, but the contact area in the first case is just the surface of your shoes here. But the second case, see you have the ski board here, right? It's way larger than the first. So the pressure in the second case is way smaller on the snow. It's way smaller than the first case. So that's why you can stay on top of snow in the second case while it goes in. So this is a small p case. This is a large p case. Okay. And actually another interesting example is a so-called, see this bed of nails. Okay. So if you actually go to like the science museum in Oklahoma City, and there's a couple other museums, they have some bed of nails you can use here. Well, the idea is you have a bunch of nails that make up a bed like this, and you can definitely lie onto it. Okay, you can lie on it like this. Well, even though they're nails, you don't really they do not go into your body. It is because your whole weight is kind of spread out. So if you add all the surface areas together, all these nails together, they have a pretty decent surface area. So the pressure is not actually very large. Okay, well, so you're good. Well, consider this another case, right? Imagine you have only 2 nails underneath yourself. Okay. Well, as you can imagine, right, this is not going to end up good. Probably going to be, you got some blood or something, you know, because in this case, instead of having thousands of nails underneath, you only have 2 nails. So the surface area is significantly smaller than the second case. So this is not good. So this is you have a really large pressure, large P and small p, okay? So this again tells you why this quantity P is useful, important, because a lot of cases, the force that you have are kind of same, but you want to reduce the pressure in order to keep yourself safe or to achieve certain functions. So that's the 2 examples, okay? Well, there's another thing you can talk about, same idea. Say in the winter, right, you go to on the frozen lake, and then this is ice, right? Then suddenly you realize the ice is not thick enough, so it's starting to break because of your weight. What you do? You should try to lie on the ice, okay, and then crawl a little bit towards the bank. And again, why do you do that? Okay, again, what are you doing here? Try to reduce your pressure, okay. Again, in this case, there's only 2. The surface area determined by the screw. Well, if you lie down, you have the whole body as the surface area. So you increase the surface area at least like 10 times. So the pressure becomes 1/10. So it's very way more unlikely that the ice is going to keep breaking when you lie down like this. Okay, compared with this case. So again, that could be really useful. This is the cracking on the ice. Okay. So let me see whether I think that's sufficient. That's not both these quantities are pretty simple, and there's a you can do some let's see calculation here for the pressure, but I think it's basically using the definition of pressure like force divided by A to calculate it. So you can take a look at the example 9.1 if you want to, but it's pretty simple thing. Okay. So next topic, let's talk about pressure in the fluid. Okay. And that's probably the most the first important thing in this chapter. So the most important thing for pressure in the fluid is the pressure is not a constant in the fluid. Okay. Well, because the fluid is actually going everywhere, so the pressure actually can go everywhere as well. So it's like if you have, say, for example, you have a tank of water here. Now, which direction does the pressure go? Well, it depends on which surface you talk about. If you draw a surface like this, the pressure will go always perpendicular to the surface. It's gonna go like both sides of it. Okay. But if you have a surface like this, the pressure is gonna go like this. So the pressure is kind of go. It really depends on what surface you have. Okay. So the most important thing for the pressure in the fluid is it depends on the depths of the fluid. Okay. For this purpose, let's consider a cube or rectangle box inside the fluid. Okay. So what we can say here is there's definitely pressure because it's a rectangle box. So there's a pressure from all the surfaces, and there's a perpendicular to the surface and going into the surface from the water. There's pressure from all these 6 surfaces. Okay. So roughly speaking, we have pressure from here, from here, from here, from here, and from top and bottom. Okay. Well, all the side pressures, they will cancel out exactly because the surface areas are equal. So for whatever pressure you have from the left, then you have whatever pressure on the right. So the force is going to be canceled out. So that's fine. But let's focus on the pressure from the top and bottom. Okay. I'll call this one P top. Okay. So on the top, you have the force from the top is given by the pressure on the top times the surface area A. And from the bottom, you have F bottom equal to pressure from the bottom times, again, area A, right? Now, if you do free body diagram for this object, on the vertical direction, you have 3 forces. Okay, first of all, you have this F top going down. And then you have F bottom going up. But remember, there's always gravity, so there's going to be weight as well going down. Let me call it mg here, okay? And because this part is this box. Okay, let's just say this is the box of water you have. Okay, so this is just water. It's just part of the water. So this water certainly can stay at rest, and it is actually staying at rest for most cases. So there's no gravity, there's no acceleration on this water. So the 3 forces have to balance each other. So you have F bottom minus mg minus F top equals 0. If you plug this into there, you have P top times A minus mg minus P bottom times A equals 0. Okay. Now if you move this term to the right and divide by A, you have P top. I'm sorry. I got it wrong here. This should be this is opposite. This should be P bottom. Okay. This should be P top. Okay. So you have a P bottom minus P top equals to mg over A. Okay. So you see there must be a pressure difference on the top of this part of the water and at the bottom of this part of water. Okay. The reason for that is because water itself has weight. In order to balance, hold the water there, you need to have a larger pressure from the bottom than the pressure from top. Okay. So, and if you write this more carefully, we can write like I'll simply call this PB minus PT. Okay. Bottom minus top, okay, equal to this. I can write this M as rho, which is the density of the water times the volume divided by A, right? So, but what is B divided by A for this cube here, right? For the rectangle box, volume equals to A times H, where H is the height of the volume of this box. So we end up with a very important formula here: PB minus PT equals to rho Hg, okay? So that's a very important formula. It tells you the pressure difference, okay, of these, the two surfaces, okay? Now the way we derive this formula is kind of specific, but actually it's a very general formula. We can apply it to almost every cases in the fluid. For example, if you consider say you have, let's say the C, okay, the C here, okay. Well, if you say on the top of the C, what is the pressure on the top? Well, it's P top, right? There's no fluid anymore here, but there's air pressure. So the air pressure is normally called P naught, okay? Air pressure. This is the pressure in the atmosphere you have, okay? So that's normally we call P naught, which is 1.01 times 10 to the fifth Pascal, okay? This is the unit we just learned. So in this case, the pressure in any given position here equals to, if you plug the P top for the air pressure, it'd be just like P0, P naught plus rho Hg, okay? This rho here is the density of the water here. Well, the H here is the depth of the water. So this actually gives you a measurement, of the how the pressure changes when you go to certain depths of water. And as we know, if you go scuba diving, right? As we know, human beings, we cannot go beyond certain depths of water, okay? Without like a very, very, we just use like without wearing something like a very solid, like a iron or metal suit or something, because the pressure is going to be proportional to the depths. The deeper you go, the bigger the pressure will be, okay? And it goes pretty fast. So, for example, let's say if you go to 100 meters here, right? If you plug in those numbers here for the water, let's use the water pressure here for H equal to 100 meter. So rho Hg equals 1.0 times 10 to the third kilogram per meter cube times 100 meter times 9.8 meter per second square. Well, this is roughly 1,000. So yeah, so this is like a 1.0 times 10 to the 6. Okay, this is gonna give you the unit of kilogram times kilogram per meter square and second square, which is just basically, essentially just that. That's just the okay, there's another meter here. Sorry, there's a meter. Okay, meter. This is just unit for Pascal. So for 100 meter depths, you have about 10 to the 6, okay, Pascal. Okay, so that's like already like 10 times larger than the atmosphere. So if you feel like the atmosphere is pretty, this is like 10 times larger than that. So it's pretty big, basically. Well, the atmosphere, the pressure, we don't feel it. That's because there's air everywhere. Okay, there's air inside of us, outside of us, so we don't feel this air pressure, except in some very special cases. So, for example, when the plane takes off from the airport, okay, when the plane goes up, you feel like kind of uncomfortable on your ears, right? The reason for that is there's a sudden change of the height. So the pressure actually decreases when they go higher. And that is actually, that makes you like the sudden change, your body is not adjusted to the new pressure. So you feel like uncomfortable on your ears. Same thing when you drive in the mountains, sometimes you go really high or going really, really low. When you change, there's a sudden change of latitude, you feel that pressure as well. Well, the same thing goes to the air, okay? So if you're on the surface of the earth, right? This is the surface of the earth. We know there's air above us and there's an atmosphere, something called atmosphere. There's a certain atmosphere here. So where does this air pressure come from? Again, we can use this formula to calculate it. Well, on the top of this, certainly there's no air, right? So the P top here would be 0. While the P bottom here, this is your P top, this is your P bottom, okay? While the P bottom here is actually the P naught we're talking about. So the P naught, roughly speaking, equals to P top plus, which is 0, time plus rho Hg. But this rho here is density of the air, right? So from there, you can calculate the air pressure as well. So the density of the air, as we know, is given by density of air is 1.29, okay? So 1.29 kilogram per meter cube. What about the height of the atmosphere? Okay, you can find it. So roughly 480 kilometers. Okay, so times 480 kilometers, or a meter. Okay, times 10 to the third meters. Okay, and then times 9.8. Okay, meter per second square. Okay, well from there you can kind of roughly estimate this P naught we have. Okay, so let me do a calculation. Use the calculator. So 1.29 times 480 times 9.8, and then we have a 10 to the third, right? So you got basically this is 6.07 times 10 to the 6, okay, Pascal. Well, this estimate was not really good estimate. I got a question here. Oh, okay. Yeah, that's fine. Okay. I'm going to answer the question after I finish this. So as you see here, I got a really large pressure compared with this one. Okay. Now the reason for that is actually air is a gas, so it's not like a liquid. Liquid is kind of, most liquid is incompressible, meaning that the density of liquid stays roughly constant. Well, gas is way sparse than liquid, so it's actually compressible, meaning the density here is not really constant. Turns out that as you go up, the density of the air is not 1.29. It's getting smaller and smaller and smaller. So this density is mostly for the density around the surface of the earth. So you got a number actually going to be way smaller than this number. So you get a real smaller number compared with this value we estimate. It turns out that the pressure we have is about 1.01 times 10 to the fifth instead of this number that we estimated. Okay. So, but anyway, you see how this formula works. Okay. And again, we don't have time to do it, but there's some exercise you can do for this pressure difference. So like normally I would do like maybe try to do example 9.2. That would be a good example for. I mean the car lift is kind of similar, but yeah, focus on example 9.2. Okay, we don't have time to do that, but let me write it down. Example 9.2. Okay. Well, the first part here, you can do this part. You can do example 9.1. Okay, here I got a question a minute ago. So the question is, how are we supposed to label the units for radius? Is it radians? Certainly it's not. Radius is a length. So the unit is meter, okay? Radian is for angle. not for the radius, okay? If you have angular speed, it's in radian per second, okay? But radius is just the length, okay? It's just like meters, okay? So we're done with this pressure difference, okay? And again, as I said, it's important. I mean, if you do this example, you probably can see a little bit better some other example. You can also do some exercise. Now let's move on to the last one, okay? Number 4, yeah. Buoyant force, okay? And this one actually is not totally new. So this is actually, okay, we don't need this pressure measurement. So buoyant force and Archimedes principle, okay? This is totally new. I mean, sorry, this is not totally new. It's related to what we talk about. So what is a buoyant force, okay? It's a very important thing, right? So sometimes we can call it Archimedes principle. So the buoyant force is something when you take a bath, you know, maybe as a kid, you notice when you throw something into the bathtub, right, with water, certain things flow on top of it, like something like a rubber duck, or something made of plastic or something. But something else will fall directly to the bottom, right? Like you have a metal piece of stuff, you know, they fall to the bottom. Okay. So the question why certain objects flow on top of it, well, some other objects sink all the way to the bottom. Okay. Well, that is actually because when you're in the fluid, there's something called the buoyant force. Okay, and then the buoyant force is related to the density. So that's why you have the difference here. So what is a buoyant force? Okay, there's actually nothing special. We can use the same idea we just learned from here. So this time consider a tank of water. Now consider not a rectangle box of water itself, but let's say you put something into this box, into the water, right? You have an object into the water here, okay? Now you want to calculate the buoyant force on this object, okay? How do you calculate it? You can use the idea of pressure difference here, okay? Again, all the pressure from the side will cancel out. Well, there's the pressure from the top and pressure from bottom. That's gonna be giving you the difference here. So the pressure on the top, as we know, is given by, okay, the difference between them, okay, okay, let me write it like this, okay. So basically you have force from the top, right, F top, and then force from bottom. That's basically coming from the pressures, right? So the buoyant force, FB, essentially equals to F bottom minus F top, okay? Which is actually equals to P bottom times A minus P top times A, right? Well, as we know, this is P bottom minus P top, okay, times A. What is P bottom minus P top? We already have this formula here. It's given by rho Hg. So let's plug in that. So we have rho times H times G times A, okay? So H times A is nothing but the volume. So in the end, you got this rho V and G, okay? So the buoyant force is given by density times volume times G. But it's very important to realize that this density here is not the density of the object, but the density of the fluid, okay? So let me write it here like fluid, okay? And the volume here actually is gonna be the volume of the object in the fluid. So I'm gonna write volume V fluid as well, okay? And then you have G here. So that's the formula for the buoyant force, okay? And again, as I explained, this is not totally new. This is because this is just come from the pressure difference of the liquid you have, okay? Now, this force was first discovered by Archimedes, okay? Let me, hopefully I can find a picture of it. Okay, now here. Archimedes was he was the first guy who discovered this buoyant force, okay? So, let me see. So Archimedes, he lives in ancient Greece, okay, long time ago, 2,000 years ago. So at that time, there was no Newton's law. There was no Newton's universal gravitational attraction. How did he discover this? Okay. Actually, it's a very interesting story. He actually discovered this by, he was assigned a job from the king. The king actually had a crown made by goldsmiths. He gave the goldsmiths a bunch of gold, and he asked him to make a crown out of it. Okay. Now he got the crown back. Okay. But he doubted that the goldsmiths didn't use all the gold he gave to him, but use something else, okay, to make the crown. Okay. So he want Archimedes to find out whether this crown is totally gold or something else. Okay. Well, without breaking the crown. Okay. Well, if you can break into pieces. You can check. Maybe you can find out there's some other material in there. But certainly that it's going to be a waste if the crown is made of gold, right? It's going to ruin the crown. So he doesn't want to ruin the crown, but also find out whether it's made of gold. So it's a very challenging job for Archimedes. So Archimedes was thinking about this problem. One day he go back to home, and then he wanted to take a bath, you know. So he stabbed one of his feet into the bath, and then he observed certain amount of water going out of the bath. Okay. Well, at that time he realized there's a smart way to figure out this. So he was yelling Eureka or something. I forgot about it. Eureka. I think it's Eureka. Eureka, Eureka. Meaning like I found it. So his idea is actually really brilliant. Okay. He was saying the following. Okay. He was saying, suppose you have some water. I mean, without any object, just water itself, right? Because the water is balanced, so all these water like if you take some arbitrary piece of water, there must be a force balancing the weight, which is a buoyant force. Okay. Well, how big is the buoyant force? Because water is at rest, so the buoyant force must equal to the weight of the fluid itself. Okay. So now he's saying that if I replace this amount of water or the fluid by an actual object, this object will feel the same same amount of buoyant force. So the buoyant force still equals to the weight of the fluid. So basically what he's saying here is that the buoyant force just equal to the weight of the fluid with the same volume. And he observed this by noticing when he put his foot in it, same amount of water will be getting out, because if he replaced the water by his foot, same volume water will come out. So, so this might help you to understand this buoyant force. It always equal to the weight of the fluid with same volume. Okay. So if you have something flowing on top of the water, only part of it is inside the water. Only this part of volume should count. This part should not count. Okay. This is going to be your volume of the fluid. Okay. Like you used in this formula. Now, with this understanding, you can actually see whether some object flow on top, some object goes to the bottom. Okay, it's very simple. So, if you consider an object in the fluid, there are two forces: weight and buoyant force. Okay. So, if buoyant force is larger than weight, the object certainly flow on top. If the buoyant force is smaller than the weight, the object is going to sink, right? So you just need to compare these two forces. Okay, how do you compare it? For the buoyant force, right, you have density of the fluid times density, the volume of the fluid, the volume of the object in fluid times g. Well, that's your buoyant force. Well, your weight, mg, equals to the density of the object times the volume of the object times g. Okay. Now, when the object is totally in water, the volume inside the fluid is same as the object, the volume of the object. So these are the same. So essentially, you need to compare just the density of the fluid to the density of the object. These are the critical things. Okay? So the density, if the density fluid is larger than density object, the buoyant force would be larger. So the object is going to flow on top. Well, if the density of fluid is smaller than the density object, the buoyant force will be smaller than the weight, so it's going to sink. It's that simple, okay? So the rubber and plastic, those stuff, their density are smaller than the water, so they're going to float on top. Well, metals are heavier than water, so they're going to sink to the bottom, okay? Does that make sense, you guys?
Yes.
No, you may wonder why, for example, right, we have ships made of metals, right? Those big ships, they're all made of metals. How come they float on top of water instead of sinking? Well, the answer is actually they're not totally metals. Okay, the shape has a lot of empty rooms in it. Okay, so the total, the equivalent density is actually way smaller because there's a density of air and density of metal average. Okay, if you just have a solid piece of metal, it's going to definitely sink to the bottom. Well, the ships float on top because there are a lot of empty rooms inside. So that's the difference. Okay. Well, another case you can explain is like people swimming, right? So we actually, as you may already know, human beings, like 70% of us is actually water. Essentially, that's because all the lives on the earth came from the sea, the oceans, right? So most part of ours are still like water. So there's only 30% of us is not water. So our density is actually pretty close to density of water. So they're so close such that if you breathe in air to your lung, okay, and your density is going to be smaller than density of water, so you can float on top, okay? And if you breathe out all the air, you have no air in the lung, you're going to sink, okay? You can dive in if you breathe out, okay? Breathe out. And breathe, this is a breathe in, okay? So that's why we can swim, you know, we can stay on top of the water. So even if you don't know how to swim, you should feel confident that if you breathe in, you should be able to float on top of water, okay? Well, I guess the real matter here is even in that case, if you're not careful, it's not like your proper part is on top of water. You may end up with like your leg on top, you know. Well, your head is sorry. This is not doesn't seem like that. Your head at the bottom. Then that's not useful, right? See, one part of you is on top, but you're gonna get drowned because the important part of yourself that you need to keep raising is underneath. So then you're gonna finally get drowned. So the skill of swimming is to make sure you have the proper balance yourself. So you have a proper part, which means like your mouth and your nose on top of water, so that you can breathe in and out on top of water. So, but overall, our human bodies are kind of really close to the density of water. Okay. Now, with given this information about the buoyant force as a new force, you can solve a lot of problems with it. Just like Newton's law problem. For example, in this case, you have this example 9.5, which is essentially how Archimedes did when he tell whether this thing's made of crown. Basically, he measured the weight of the crown in the air and in the water, and from there he could figure out whether the density of the crown is the same as density of gold or not. Okay. Well, based on that, he told the king that the goldsmith indeed took away a certain amount of gold. So the king actually killed that goldsmith. So, but that's another story. So there's I think example 9.6 is also very good because in this one, you have only part of the objects is floating on top of the water. So you can see that how you calculate the buoyant force using only the volume of the part of the body in the water. So both 9.5 and 9.6, I think, is worth to study. Okay. Example 9.5 and example 9.6. Okay. So, and that finished the lecture about chapter 9. I'm kind of going through everything pretty fast because we only have this one lecture for that, and also because this is not going to be tested and we don't even have a homework for this. This is just for some people who want to take MAMCAT, kind of help you to kind of see what's being talked about in this chapter. Now, we don't have time to talk about the further sections, like the fluid in motion part. I think this is relatively unimportant compared with the fluid statics, which we just talked about today, because normally fluid in motion is more difficult than fluid at rest. So I don't know whether MCAT include this part, the fluid in motion, but basically the important thing is equation of continuity here. And also the Bernoulli's equation, which I think, yeah, like this one here, but normally they're more complicated. So, and like other application, this is, I think, is even more complicated. Yeah, there's all kind of interesting about fluid, you know, like surface tension and stuff, but it's just we don't have time. Capillary action, et cetera, et cetera. They're all interesting. Okay? I think these are all pretty much all pretty complicated. Reynolds number and stuff. These are pretty complicated. So that diffusion is even more complicated. I doubt they're going to be on the MCAT, but
yeah, MK has all of this.
all of this, okay.
Yeah, the complicated part.
Yeah. We normally, even if we have time, we normally don't cover fluid motion. But I would say in each case, focus on the principles. Like what I said before, for fluid motion, focus on the continuity equation here, and also the Bernoulli's equation here. And then when you go to like other applications, like these are definitely complicated, you know, the lift force or something. I mean, the surface tension, honestly, I don't know how they test it, but well, you just need to understand there's certain things like surface tension you can calculate like this, you know, it's a simple equation, but I don't really think they're that.
They tested this with the blood flow.
Oh, I see. Okay.
Yeah.
So blood is certainly very viscous. Oh yeah, because blood is fluid. Yeah, I see. I mean, capillary motion action. I honestly think is a well. I don't know. Viscous fluid flow maybe is useful because the blood is actually the flow of blood inside the vessel. Maybe it's very viscous. I mean, it's not given. Oh, the blood is given here. So, see, the viscosity is 2.7. See, it's way more viscous than water. So it's like at least 3 times or even more. So, well, there's I mean, this will take like forever to explain everything here. Yeah, I guess for you guys, maybe you need to know some basic equation like this, you know. But to understand the physics behind it is actually, we really need the Navier-Stokes equation from fluid mechanics. Well, the diffusion, you may want to know, again, some basic formulas as well. Maybe like this one. I mean, this is called Fick's law. You may understand that. So yeah, there is one about the floating of blood. I guess, how about this? I mean, if you need something, when you face a problem or something, you can send me email. Even after we finish the semester, you can ask me any question you want, you know.